Okay. Good morning. My name is Daria Carter, and today I'm going to be talking to you all about corrosion. So last semester I took Dr. Park's Corrosion Science and Engineering course, and I thought it was pretty interesting. So that's why I'm going to talk to you all about it today. I know it's a very broad topic, but I'm going to just try to keep it to some main points to put it all in a nutshell. So here's an outline of what I'll be talking about today. First, we're going to start off with an introduction to corrosion. Then we're going to talk about a few of the common types of corrosion. Then I'm going to talk about how corrosion is related to thermodynamics. And I'm going to show a few pictures of some corrosion issues in industry, and then I'll wrap it up with the conclusion. So first, what is corrosion? Corrosion is defined as the degradation of metals due to its environment. So metals, pure metals, are actually extracted from ores, and they're chemically bounded to these ores with like sulfides and oxides. So once these pure metals are extracted from the ores, they're taken to a higher energy state, and naturally in nature, things want to be at the lowest energy state possible. And this is actually what the corrosion process is. It's taking something from a higher energy state to a lower energy state. There are 4 components necessary for corrosion to occur. First, there has to be an anodic reaction, which is where there is a loss of electrons. So this is also where the corrosion takes place. As you can see here, we have steel, and that's the iron oxide. There also has to be a cathodic reaction, which is where the electrons from the anode are traveling to. It's traveling to the cathode, so it's gaining electrons. You also have to have a metallic path of contact between the anode and cathode in order for the electrons to transfer. And then finally, you must have the presence of an electrolyte, which is usually water, but it can also be some other sort of aqueous solution. So these are a couple or a few of the types of corrosion that I've decided to put on the PowerPoint. So first, I have uniform attack corrosion, which is pretty much where the metal is being attacked all over the surface. Then there's also stress corrosion cracking, which is a combination of applied stress and applied stress in a chemical environment, and it causes cracking on the metal surface. There's also pitting, which is corrosion that happens at fixed points, so it's localized. And then there's galvanic corrosion, which is when you have 2 metals that are in contact with each other, and one metal is going to corrode in preference over the other. So corrosion and thermodynamics, there's a relationship, of course. So Gibbs-free energy can pretty much tell us if a reaction can happen or not. Gibbs-free energy, as it relates to corrosion, represents the free energy change for an electrochemical process. So there I have the Gibbs-free energy equation as it relates to the electrochemical process. We have delta G, which is the free energy. It's equal to N times F times E, which is the number of electrons transferred. F is Faraday's constant, and E is the electric potential difference. We also have the equation with naught that represents the standard state equation, and E naught is actually a value you can find inside of on the EMF tables, which stands for the electric motor force. So the Nernst equation correlates Gibbs-free energy with electric potential. So it tells how the cell potential varies with the standard state, with the electric potential at the standard state, which is E naught. And then you also have to relate it to the product to reactant ratios, which is going to be Q. So in a corrosion equation, you have, of course, the products and the reactants. And you're going to use Q, which depends on what you're actually reacting. It could be a gas, it could be a solid, or it could be a liquid. And then you can use that, your products, you're going to use the product of your products and the product of your reactants, and you're going to put it in a ratio. That's how you relate that to the electric potential. And then, of course, there's also something called the Pourbaix diagrams. So that summarizes the corrosion thermodynamic information using potential versus pH. So if you know the electric potential of a metal and you know the pH, then you can kind of determine the region it lands in. So if it's in a corrosion region, then of course it's going to corrode. If it's in a passivation region, that means that the passive layers that are caused by corrosion are being inhibited. So it means it's trying to slow it down or not cause it not to happen. And then you also have the immunity region, which means that no corrosion will take place at all. So here are just a few examples of corrosion in industry. It's very common in oil and gas. Right here I have a picture of the inside of a pipe that could have been in contact with some sort of chemicals or water. As you can see, it's degrading. So it's common in pipelines and drilling equipment. It's also popular in the automotive industry. So corrosion is a problem with, if you use ethanol, for example, ethanol actually it can corrode your engine. That's one type of fuel that can do that. There's also corrosion that can come from, or that can happen in your exhaust system. That's mostly due to high temperature corrosion. And there's also corrosion that can do with your paint coatings, which you really don't see that often, but over time, technology has allowed us to kind of alter paint chemical makeup to reduce that. And it's also kind of common in the electronics industry. I guess a lot of people don't know about that, but a lot of our computers, integrated circuits, and microchips, they come in contact with a lot of heat often, and heat is actually a factor in corrosion. So as a conclusion, again, corrosion is the degradation of metals caused by its environment. There are several types of corrosion. I only listed 4, but there's also high temperature corrosion. There's erosion corrosion, which, you know, if you have like a lot of, that's pretty common like in sea areas. And then of course there is a relationship between corrosion and thermodynamics. We talked about Gibbs free energy and the Nernst equation and the Corbax diagrams. And finally, corrosion is a problem in many industries. I only listed 3, but it's also popular in food and drink industries. I thought that was pretty interesting. So, and here are most of my references.
Any questions?
Yeah.
Did y'all study at all any methods to inhibit or kind of control corrosion?
Yeah. So of course, one simple method is just to try to keep your metals away from aqueous solutions or water, just to kind of keep things in a dry environment. Another popular method is actually called cathodic protection, which is when you have a metal that you want to actually protect, you put it near another metal that has a lower electric potential, so that way the other metal corrodes instead of the one you're trying to protect. So you look at the electric potential differences, but that's something that's pretty popular. And there's also something called impressed current control, I guess. You kind of make the current flow in a different way by introducing like a DC system. So that's another way too, that I can think of at the top of my head.
Yeah,